So this video is all about us discussing the question, what if I need to factor a polynomial of degree greater than 2? Remember, degree is the power of the leading term. So this function here, or this expression here, is a polynomial of degree 3. So we have all these tricks that we've learned about factoring quadratics, right? Ones that are degree 2, like x squared. But we should talk a bit about how do I factor a polynomial, which is higher degree, right? So to start things off, I kind of want to explore this idea of factoring this polynomial. And then through that exploration, we will have kind of proven and hopefully have a greater understanding of what's called the rational zeros theorem. All right. So to start things off, let's think about what this will end up looking like when I break it up into its factors. This polynomial here is degree 3. So it should have, well, we hope it'll have potentially 3 factors, right? It could have less potentially depending on how the factors are, but let's for now accept that we're kind of looking for 3 factors, right? And factors of a polynomial tend to be of the form like a x plus b, right? This is what factors tend to look like. It's like some x term and some number term kind of adding or subtracting each other, right? What I'm going to do is I'm going to call this a1 and b1, all right, just to distinguish them, because I'm going to call this factor is going to then be a2x plus b2 and a3x plus b3. Essentially, I'm using these a's and b's as just placeholders for the coefficients and constants which could be in my factors. But the main purpose is that, okay, this function could be broken up into 1, 2, 3 pieces multiplying, right? So what I know is that when I have all these factors, all 3 of the x terms should end up multiplying a1 times a2 times a3 x cubed, right? See how if all these multiplied, I'd have a1, a2, a3, and 1, 2, 3 x's, so it's x cubed. These all 3 multiplying should end up making the same thing as my leading term, 3x cubed. Now, similarly, I can notice that all of the numbers multiplied, so b1, b2, and b3, b1, b2, b3, all multiplied, should wind up equaling my constant, right? Because these are all the numbers. And in the end, they should multiply to make the constant. That constant being the number 8. So what have we learned here? We've kind of seen that when I have any polynomial, I can use the leading term to know what all of my possible x terms in the factors would be, right? And I can use the constant to know what all the constant terms in the factors would be. So this gives me a cool list of these possible terms for my factors. So all of the x terms here, a1x, a2x, a3x, they should all be some sort of factor of 3x cubed. Particularly, I care about that number 3 there. What are the factors of 3? 1 and 3. So the factors of 3x cubed are x and 3x, right? These could all have been either a single x or 3x. Now let's look at the constant 8 here. This is going to determine all of the possible constants in my factors. So my constants in my factors could be the factors of 8. That's 1, 2, 4, and 8. So knowing these 2 lists of factors, I can then make a combination of the one x term with one factor with one constant to create my factors. And that's going to give me a list of all the possible factors for this polynomial, right? So I'm not yet figuring out what the factors are. I'm merely creating a list of what all the possible factors are. So it could be x plus 1, x plus 2, x plus 4, x plus 8, x minus 1, right? Because it could be plus or minus in my factor. So I'm going to put that in the middle, plus or minus. So it's like x and 3x are on one side, and 1, 2, 4, and 8 are the other piece of my factors. So let's write that out in a list, actually. What are all the possible factors for this polynomial? It's x plus 1, x minus 1, x plus 2, x minus 2, x plus 4, x minus 4, x plus 8, x minus 8, 3x plus 1, 3x minus 1, 3x plus 2, 3x minus 2. You kind of see what's going on here, right? 3x plus 4, 3x minus 4, and 3x plus 8, 3x minus 8. So that is all of the possible factors for this polynomial. Very nice. Now, each of these factors is going to actually have a corresponding 0 for it, right? The 0 being the value of x, which makes that factor equal to 0. So from that, let's go ahead and create a list of all the possible zeros, right? Because that'd be all the x-intercepts for this function, also known as all the solutions of the function, right? All the roots. So looking at these, the possible zeros would be -1 and +1. So it'd be like x equals plus or minus 1, plus or minus 2, plus or minus 4 from the x plus and minus 4s. From this one, I'd have 8. Ooh, 3x plus 1. What happens when 3x plus 1 equals 0? You subtract 1 from both sides and divide by 3. So you get x equals -1/3. So plus or minus 1/3. If I have 3x plus 2, then the root is 2/3. 3x plus 4, it's 4/3. And 3x plus 8, 8/3. So this here is my list of possible x solutions for this function if it was to be equal to 0, right? If. And the reason why I say if it's equal to 0 is because, why do we factor? It's to solve when a function is equal to 0. Cool. So all this is to say this list. All this stuff I've been talking about is literally for us to get this list of possible zeros. Why do we want this list of possible zeros? Because this is actually the rational zeros theorem. What is rational zeros theorem? Rational zeros theorem says if you have any function f of x equals ax to the power of n plus ... plus b. Sorry, I'm not going to use a and b. We've already used a and b. Let's use new variables. Let's use p and q. All right. So p is the p is just being a placeholder for the leading term, the leading constant, and q is the placeholder for the constant, right? Coefficient, I mean. So what happens if I have a polynomial which is of this form, right? Where p is the leading coefficient and q is the constant. I can know a list of all possible rational zeros. This is a list of all of the possible x values which make the function equal to 0, which are rational. Remember, guys, a rational number is any number that can be written as like a over b. Any number that can be written as a fraction, and technically 1 is a fraction, those are all rational numbers. So what are the possible rational zeros for this polynomial where I have p x to the n plus dot 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 plus q? Well, it's going to be equal to a combination of all of the factors of the constant, right? See how the constant, the factors of 8 were all of our possible x values on the numerator. So the factors of q, because that's my constant. I probably shouldn't underline that. That looks kind of whack. And over the factors of p. So let's look at this, right? The factors of q. The factors of 8, right? The factors of q are 1, 2, 4, and 8. Look at our possible x values here. 1, 2, 4, and 8. 1, 2, 4, and 8. The bottom, the denominator, are the factors of p. That's the leading coefficient, which is 3 here. What are the factors of 3? 1 and 3. Technically, all these whole numbers are actually over 1, right? And then all these ones are over the value of 3. So essentially, guys, by knowing the factors of the leading coefficient and the constant, I can know a list of possible rational zeros. That's rational zeros theorem. All right, so now you might be like, okay, Mr. Hobaugh, this is cool and all. We got this list of potential zeros. What does that even mean? Why are they potential zeros? You telling me that these aren't actually the zeros? No, these are not all the zeros. This would be ridiculous if these were all the zeros. We could not possibly have 16 zeros for a degree 3 polynomial. It could only have up to 3 solutions for the x value. So what we need to do now is we need to test the zeros. All right, we're going to test them. Okay, how does one test a zero or a potential zero? Well, guys, what is a zero supposed to do to a function? What is the zero of a polynomial? Or just the zero of any function? The zeros of a function, or an expression, a polynomial in this case, are just the values of x, right? Like, let's say this is f of x. The zeros are the values of x such that f of x equals 0. It's just what do I plug in here in order to make the whole thing 0, right? So it's actually pretty easy to test it. All you have to do is plug them in and see, does it equal 0? The most efficient way to do this, y'all, is to create a table. So I really recommend make a table, okay? Make a table, do this. Because I promise you, it'll make your life so much easier to do this. So we're going to be testing different x values, and we're plugging them into these 4 terms: 3x cubed minus x squared minus 10x and plus 8. And then the question is, what is f of x? So you guys see this table I've created? Okay, cool. So I like to start out plugging in 1 just because 1 is extremely easy to plug in. And if you find that it works, that's awesome. So I'm going to plug in x equals 1. So when I plug in x equals 1, what is this equal to? 1 cubed is 1 times 3 is 3. 1 squared is 1 minus 1. Negative 10 times 1 is minus 10. And plus 8 is plus 8. Doesn't matter what x is. So I go ahead and add these all up, and I say 3 minus 1 minus 10. So minus 1 minus 10, that's minus 11. 3 and 8 is positive 11. Does this equal 0? It does equal 0. And in fact, as soon as you find one x value that works, as soon as you find one that equals 0, stop. Don't even bother continuing to test plugging in any x values. You don't need to plug in any more x values once you've found a single one that works. Because what we're going to do is we're going to then use that. We're going to use this 0 to solve the rest of the problem. All we needed to do was find a single one that works. With that said, for the sake of us practicing, let's say this one didn't work and I wanted to find a different one. I'm going to just keep going just because I think it's good for us for the example. So, okay, I plug in the next thing, which would be -1. So I'm going to plug in -1. What's awesome about making this table, when I plug in a negative value of one that I already have, all these numbers are going to stay the same, except some of them will flip their sign. Some of them will become negative, right? Because what's -1 cubed? That's -1 times 3 is -3. What's -1 squared? It's +1 times a negative is -1. What's -1 times -10? +10, so +10. And +8 is still +8. So do you guys see how all the odd powered terms, right? All the terms with an odd power of x just flip their sign, and all the ones with either no x or an even power of x stayed the same. Does -3, -1, +10, +8 equals 0? No, it doesn't, right? I can very easily tell that this does not equal 0. In fact, I don't even care what it equals. All I know is that it does not equal 0. Let's say that I wanted to keep testing them. Let's plug in 2. 2 to the power of 3 is 8. 8 times 3 is 24. 2 squared is 4. Times minus is -4. 2 times 10 is 20, so -20. And +8 is still +8. 24 minus 4 is 20. Minus 20 is 0. +8 is not 0. What about -2? Well, using the trick that I just explained earlier, I know that all that's going to happen is the odd ones are going to switch their sign. So this will become -24, +20. This will stay as -4, and this will stay as +8. Oh, look at that, dude. -24 and -4 are -28. 20 and 8 is +28. Together, this should make 0. Let's just assume for now that this one we didn't see. Okay, we didn't see this one. We didn't see that. We're going to stick with this guy. Let's stick with this guy. So, roll camera. Awesome. We found one of the x values, one of these rational zeros, which works. It's -2. So now I'm going to stop because I found one and go on to the next step. All right, so I know one of the rational zeros. What do I do with it? Well, since we know the 0 of the polynomial, we can know one of the factors, right? What factor has a 0 at x equals -2? X plus 2, right? Because x plus 2 is equal to 0 when x is -2. But what about the rest of the polynomial? What is that? I only know one factor. Well, we can actually now solve for the rest of the polynomial. And I kind of want you guys to follow with me. Why is it that I'm going to do what I'm about to do? Think about it like this, right? My polynomial is equal to x plus 2 times something else. What is that something else? I don't know. Well, how can I find out what that something else is? I can solve for it using algebra. How do I get the rest by itself? I divide both sides by x plus 2. As one does in algebra, right? If something's multiplying what you want to know what it equals, if something's multiplying your thing that you want to solve for, you just divide it. So all we have to do to find the rest is divide our polynomial by x plus 2. This is a method known as polynomial long division. You may have seen it in Algebra 2. You may have done something called synthetic division in Algebra 2. I do not want you to do synthetic division. Now, I know some people are going to not like that. Some people love synthetic division. And that's cool and all. But I want y'all to learn how to use polynomial long division because it's an important skill and it's so much more useful than synthetic division. Synthetic division is I'm not gonna rant about synthetic division right now. All right, so how do we do polynomial long division? It's actually pretty easy, guys. It's really similar to how you do normal long division. What we're gonna do is this. We're gonna say, okay, well, I need to have 3x cubed. how do I turn x, right, my leading term here, into 3x cubed? I got to multiply it by 3x squared, huh? Right? So I know that x can go into 3x cubed 3x squared times. It's kind of like how long division works. And then what I do is this. I say, okay, well then I multiply 3x squared into my x plus 2, and I get 3x squared times x is 3x cubed. 3x squared times 2 is 6x squared. And what I'm going to do is I'm going to subtract this from my numerator. Why am I subtracting? It's because I'm essentially saying like 3x squared has this much covered, so I can get rid of it. So 3x cubed minus 3x cubed cancels out. That's good because that's what we wanted. Minus x squared minus 6x squared is minus 7x squared. Okay, now we can go to the next piece. What do I need to multiply x by to get minus 7x squared? Minus 7x. Negative 7x times x is minus 7x squared. Negative 7x times 2 is minus 14x. And I'm going to take this away again. Negative 7x squared minus 7x squared. When I do a double minus, it adds, right? Effectively, this is going to become plus 7x squared plus 14x. So these will cancel. And negative 10 plus 14 is 4x. Excellent. See what I did there? Now, how many times does x go into 4x? It goes in 4 times. 4 times x is 4x. 4 times 2 is 8. And I subtract that. 4x minus 4x cancels out. 8 minus 8 cancels out. And I am left with 0, which is perfect. What that means, guys, is that I have a remainder of 0, meaning that this was a perfect division. Therefore, what I've shown here, guys, is that the rest here is equal to 3x squared minus 7x plus 4. So what we've done here, y'all, is once we knew what one of the factors of the polynomial was, we divided it out of the polynomial to know what the rest of the polynomial should be after it's been factored, right? If you guys think about it, factoring is actually basically just division. So rewriting our whole expression here, I'm going to move on over to the right. What we see is that our original polynomial, 3x cubed minus x squared minus 10x plus 8 is equal to x plus 2 times 3x squared minus 7x plus 4. Excellent. And hey, look at this, guys. Once you've factored out one of the factors, it lowers the power, it lowers the degree by 1. I now have a quadratic. At this point in time, guys, I can factor this just using quadratic factoring methods, like the diamond method, or I like to use what I call the double cheek. The double cheek, if you have not seen it yet, is this idea where I just take a quadratic and I draw 2 cheeks, right? I draw my 2 parentheses because I know that this quadratic will break up into 2 factors. And I kind of go big brain mode and just try to think about what the factors should be, right? What would make 3x squared? It's just going to be x and 3x. That's all it could be, right? I know it could only be x and 3x. The numbers, what could they be? They have to multiply to 4 somehow. And they have to add up in the end to minus 7. I think that's going to end up being like minus 1. Because minus 1 times 3 is minus 3, and minus 4, because minus 4 times 1 is minus 4. Minus 3 and minus 4 makes minus 7, and they multiply to make positive 4. Now, if you don't want to do this, you are totally welcome to do the diamond method. 3 times 4 is 12 on top, -7. What multiplies to 12 adds -7, -3 and -4. And as you go through and do the factor by grouping, you should see that you get 3x times x minus 1 and -4 times x minus 1. And so it would be x minus 1 and 3x minus 4. Awesome. And look, we have factored this higher degree polynomial. Isn't that crazy, y'all? That's crazy. Now, I know factoring higher degree polynomials looks like a lot of work. It is. Let's be real. I'm not going to sugarcoat it. It is a good amount of work. And I'm not going to really ask you guys to do it like constantly. But it is a skill that is it is actually quite useful. I think it involves a lot of very practical applications of the math that we kind of know already, but in creative ways that we've not done before. I'm going to go ahead and do one more example in this video, and then y'all will be able to do your notes check. All right, so sometimes my students complain that the examples I do in my videos aren't hard enough, and then the problems that I give them in the homework or whatever are too hard, you know, like they don't match up or something. So here's a really hard one to do, and we're going to do it here together. Well, I guess I'm doing it, but y'all, I would like to follow along, please. I highly recommend going ahead and pausing the video while we're going through the steps and you try it out yourself. So to start things off, let's create a list of rational zeros. Remember, creating the list of rational zeros, create list of rational zeros. That's our first step. So let's do it. It's going to be x equals the factors of the constant here, right? Remember, it was the factors of the constant, so factors of 12 over the factors of the leading coefficient. So what would that be? It would be plus or minus the factors of 12 are 1, 2, 3, 4, 6, and 12. Now, it's going to be all over those factors of 2. So that's plus or minus 1 and 2. So what are all my possible rational zeros? It is going to be 1 over 1 is 1. 2 over 1 is 2. 3, 4, 6, 12. By the way, all these should be plus or minus, right? They could all be positive or negative. And all these values over 2. So 1 over 2 is 1/2. 2 over 2 is 1, which I've already covered, so excellent for me. 3 over 2 is 3/2. 4 over 2 is 2, which we already did. 6 over 2 is 3, which we already did. 12 over 2 is 6, which we already did. So this is my list of possible rational zeros. What is the next step? The next step is to test the zeros. Right? Remember, that's what we're going to do here. So we're going to test the zeros. So to do that, I would like to create a table. X. And this monster. 2x to the 4, 5x cubed, minus 11x squared, minus 20x, and 12. And then the sum. This little e symbol means sum in math. You don't actually have to do that. You could have written f of x. But I like to flex on y'all with my math knowledge and vocab and shit. So let's go ahead and test them. I like to start with the ones first just because it's easy to plug them in. So I start with x equals 1. 1 to the 4 is 1 times 2 is 2. You kind of see what's going to happen here, right? It's just going to be all the coefficients. This would be 5, minus 11, minus 20, and 12. Let's think about it. Is this going to make 0? Not really, because I got negative 11, negative 20. That's negative 31. No way that this adds up to 31. Right? That's too small. So it's not 0. Notice that I don't even care what they actually add up to. All I care is that they add up to 0. Let's try negative 1. Remember my trick, guys. All the even ones, right? A negative to an even power is positive. So these will all stay the same. So this will be 2 still. This will still be negative 11. This is still going to be 12. A negative number to an odd power is negative. So this will become negative 5 and positive 20. Let's see, do these add up? 20 and 12, that's 32. Plus 2 is 34. No way. All right, next thing. So we know that x equals 1, not an option. Damn, dude, I was hoping so. Let's try 2. Plug in 2. Okay, 2 to the 4. That's, oh God. 16 times 2 is 32. 2 to the third is 8 times 5 is 40. 2 to the second is 4 times negative 11 is negative 44. 2 times negative 20 is minus 40. And 12 is still 12. Let's see. Oh, dude, look at that. Look at this. You can always do stuff like this. 40 and minus 40 cancel out. Negative 44 and 32 plus 12. 32 plus 12 is 44. Therefore, this is 0. Ding, ding, ding. I stop. Nice. Now that I have a 0, which works, I am going to factor it out of my polynomial, right? So I'm going to zoom out a little bit so I have more space. And what are we going to do? We are going to use polynomial long division to factor, just to factor. That's what we're doing. We're factoring. So we're going to use polynomial long division to factor. What is the factor which makes x equal to a 0? It's x minus 2, right? So I'm taking my original polynomial of 2x to the 4 plus 5x cubed minus 11x squared minus 20x plus 12, and I'm going to divide it by the factor which has a 0 at x equals 2. That would be x minus 2. I'm going to need to move this guy out of the way. So let's do it. What do I need to multiply to get 2x to the 4 here? I need 2x to the third. It's actually polynomial long division's not crazy hard. It looks intimidating, but it's quite fun, actually. And I mean, I know that you might be like, Mr. Hobart, math isn't fun like that. But I don't know. It's kind of mind-numbing. It's like just a process that just keeps going, right? So this 2x cubed times x is 2x to the 4 times minus 2 is minus 4x cubed. And we subtract it. These guys will cancel. 5 minus 4, that's plus. So 5 plus 4 is 9x cubed. All right, what do we need to multiply to get 9x cubed? 9x squared. 9x squared times this is 9x cubed. 9x squared times minus 2 is minus 18x squared. And we're going to subtract it. All right, these guys will cancel. You'll notice that should happen every time if we're doing it correctly. Negative 11 plus 18, that's going to be 7x squared. All right, x times 7x would make 7x squared. 7x times minus 2 is minus 14x. We're going to subtract that. These guys will cancel. Negative 20 plus 14 is minus 6x. And so our last piece is negative 6. Negative 6 times x minus 2 is minus 6x plus 12. We are going to subtract that. These guys cancel. And do these cancel? That's kind of the question, right? If these guys cancel, then it means that you did it correctly. 12 minus 12 is 0. Yay! We did it. So, what have we done so far? We figured out that this 2x to the 4 ... is equal to. I'm gonna write it down here. We found that it is equal to x minus 2 times 2x cubed plus 9x squared plus 7x. What's that last piece? Minus 6. Awesome. And that equals 0. Are we done? No, we're not done. Come on, bruh. Of course we're not done. You know what we got to do? Because I gave us a really hard example to work with. We got to do it one more time. Why? We still have a power of 3. We cannot use quadratic factoring yet because we don't have a quadratic. We have a cubic. So we got to do higher degree polynomial factoring one more time. Let's get it, y'all. But settle yourself on in here for a fun time. So let's get it. So what are the possible zeros of this guy, right? What's nice with this, guys, is that once I've factored out one of them, it does get a little bit easier. Like the pieces are smaller, right? This was a harder expression to do than this one. So let's get it. What's my first step? Let's look at the notes. Create list of rational zeros. Okay, let's create the list of rational zeros. X is equal to the factors of 6. So F6 over the factors of 2. That is 1, 2, 3, 6 over 1 and 2. That is 1, 2, 3, 6 plus or minus, and 1 over 2. 2 over 2 is 1. We already have that. 3 over 2. And 6 over 2, which is 3. We already have that. All right, time to test them, y'all. I create a table. X, 2x cubed, 9x squared, 7x, and minus 6. And my sum. Let's plug them in. As I've said before, I like to start with the ones just because they're easy to plug in. Why is that? Because look, it's just going to be all the constants. This is going to be 2, 9, 7, minus 6. Does that make 0? No. What about negative 1? Well, it's just going to flip the odd ones to being negative, so minus 2 and minus 7. And these guys will stay the same, minus 6 and 9. Does that make 0? No way, man. All right, let's try 2. That'd be crazy. What if 2 was it again, and then we just actually had x minus 2 squared? Let's see. 2 cubed is 8 times 2 is 16. 2 squared is 4 times 9 is 36. 2 times 7 is 14. All right, no way that this is about to be 0. Come on, bro. Negative 2, please? Question mark? Negative 2. So, okay. Oh, wait, remember. If it's negative, then I get to just flip these guys to being negative. So negative 16, negative 14, negative 6. By the way, if you don't feel comfortable with that, and then this will be positive 36 still. By the way, if you don't feel comfortable with this whole flipping thing, you can always, or if you just don't remember, it doesn't matter, man. Just plug it in. It's just a nice little trick to make things easier for us. Let's see. Does this equal 0? Negative 16, negative 14 is negative 30. Minus 6 is negative 36. It is 0. Nice. All right. So let's factor it, y'all. What do we do to factor it? We do the division. What is my factor? Well, what factor makes x equal negative 2? It'd be x plus 2, right? Because x plus 2 is equal to 0 when x is negative 2. What am I dividing it away from? My cubic here. So 2x cubed, 9x squared, 7x, and minus 6. All right, let's do this one. X times 2x squared is 2x cubed, and that makes 4x squared, which we're going to subtract them. I'm not going to do it like that, which I'm going to subtract. So I end up with 9 minus 4 is 5x squared. So I need 5x. 5x times x is 5x squared. 5x times 2 is 10. X. Subtract that. 7 minus 10 is minus 3. X. X times negative 3 is minus 3x. And negative 3 times 2 is minus 6. We're going to subtract that. These will cancel. What is negative 6 minus negative 6? Well, that's the same thing as negative 6 plus 6, which is 0. We did it, y'all. Okay. So what do we got? We have this. Looking at my original, or my expression that I had here, I had x minus 2 already. I'm gonna keep that, right? Don't forget the factors we've already pulled out. And then what did I pull out of this cubic? I pulled out x plus 2. And what was I left with? 2x squared plus 5x minus 3. And what do you guys know? I have a quadratic. Oh, this was supposed to be equal to 0, by the way. I have a quadratic. I can factor that real easy. This is going to be x minus 2 times x plus 2 times 2x something and times x something equals 0. What will those somethings be? The multiples of 3. This will be plus 3 and minus 1. Look at that. Yeah, because 2x times x is 2x squared. This is 6x minus 1 is 5x and negative 3. Awesome. And what do you guys know? Look, now that it's all factored, I can solve it. So what are the solutions? Well, it would be x minus 2 equals 0. That's x equals 2. X plus 2 equals 0. That's x equals negative 2. 2x minus 1 equals 0. 2x minus 1 equals 0. I add 1 to both sides, divide by 2, get x equals 1/2. And x plus 3 equals 0, so x is negative 3. And look at that, guys. I have just solved an equation for a I want to curse so badly, but for a degree 4 polynomial. Come on, man. Look at that. That's crazy. All right. So I hope that this example, this one was harder than probably any problem I'm really going to, well, maybe I will give you guys a degree 4 polynomial just to be a little evil one day. But mostly I would give you guys a degree 3 to factor just because I think it's kind of a little bit excessive to have to do it twice. But as a quick recap, y'all, since we're wrapping up the video, how do we factor higher degree polynomials? You first create a list of rational zeros using the constant in the leading coefficient. Then you test those zeros by plugging them in and seeing what makes it equal 0, right? Because that's the whole point of a 0. It's supposed to plug into the function and make it 0. Once you found one that makes it 0, we factor it using polynomial long division. And you just repeat that process until you've gotten to where you have a quadratic, which is just easy money to factor. And we've solved it. Look at us. Well done. All right. Hope y'all have a good week. Happy Halloween.